Hello. Now, we've been working with angle-angle similarity for a couple problems now. But this problem is especially special because we're going to see this exact same setup come up in the future lessons, especially regarding Pythagorean theorem. So, let's take a look at the problem. Find BC and DC given that AD is equivalent to 3, BD is 4, and AB is 5. So, first thing you should ask yourself is, well, we've been using angle-angle similarity for a while. Let's try to use it again. However, the problem being that we no longer have any parallel lines to give us some free angles to work with, free congruent angles. So that's going to be a problem. Well, let's take this figure and really look at it. We have obviously two triangles, ADB and DBC, both being right triangles because of the right angle here, and of course we would then have a right angle over there. But there is a third right triangle, that being ABC, the larger one that encompasses the smaller two. And this one is what's going to be very, very important when it comes to solving our problem. Because let's take a look. Let's say we want to work with triangle ADB. And so far we're working with similarity. So I want to show that this is similar to another triangle. Our first choice might be to try to show that it's similar to DBC or one of them. So we know that they both contain that 90-degree angle here, and again the one I showed you over there. So they have an angle in common. But since everything else is unmarked and there's no real intuitive way to see that there's any other types of congruent angles, well, we can't really do much. So let's look at the third triangle, ABC. Well, we can tell they both have a 90-degree angle. So specifically, ADB, the 90-degree angle is located at, well, ADB. Well, the other triangle, ABC, the 90-degree angle is located at the angle ABC. They are both 90 degrees. So we have one pair of congruent angles. For angle-angle similarity to work, we need to find one more. Well, what seems to be the other one that they share? Now, it's kind of obvious, but they both share angle A. Right there. Both the triangles ABC and ADB share angle A. So that means we have two pairs of congruent angles. ADB equals angle ABC, and angle A, of course, equals angle A, which means we have angle-angle similarity. Now, ADB, if we look at this triangle ADB, what do we notice? Well, the side across from the 90-degree angle is AB, and the side across from the 90-degree angle in ABC is AC. So those two sides have to match up. And if we're going to write our congruency statement, we have to make sure everything matches up very nicely. So we have angle A matching, of course, with angle A. And then, well, the angle ADB, the angle at D is the right angle, and if we look at ABC, that makes the right angle, so we can just write this statement, ABC. And that'll get us the proper congruency statement. If you're having a hard time understanding how to match the letters up, just try to imagine, alright, well, what looks like the smallest side of ADB? AD looks like about the smallest side. So AD must match with the smallest side of ABC. Well, what looks like the smallest side of ABC? AB does. So AB and AD must go together. And then you can finally put the last letters together. That's if you're having a hard time just trying to think spatially what must go together. Anyway, so now we can come up with proportions. And these proportions are always nice because they can help us figure out some of the problems. So, in ADB, let's start with the side AD. AD, again, seeming to be the smallest side of ADB. Well then, looking at ABC, the smallest side seeming to be AB. And since the triangles are similar, we must be equal to another ratio. So, the largest side of ADB would be actually AB, funny enough. And you can always tell in a right triangle what the largest side is because it's directly across from the right angle. So that will always be the largest side. Well then, what's the largest side of ABC? Across from the right angle, that would be the side AC. And finally, we have one more ratio we could write. Let me just erase some of the extra stuff. The missing side we have, so we have AD, AB, and then finally we would have BD. Well, what side matches with BD? That it's like that medium-sized one. Well, that seems to be not DB, sorry, BC. So we have the following proportions. Now let's see if we can plug in any values. So AD is 3. AB is 5. AB also over here is 5. And AC, well, we're not quite sure what that is, so we're just going to leave it for now. And then finally we have BD, which is not, I'm not just going to leave that as a variable because BD is 4 over BC. Okay, so now we can solve for one of the things we're looking for. We're trying to find BC. So I'm going to take my ratio 4 over BC and set it equal to the ratio that we know will simplify the 3 over 5 because there's no other unknown terms in the 3 over 5. So how do you solve this? Well, you can multiply by 5 on both sides to cancel the denominator, or you can use cross multiplication, whatever you prefer. I'm going to do it the long way and multiply by 5 on both sides. 5 there and 5 there. So that cancels out and we get 3 equals. If you're multiplying a whole number with a fraction, you just multiply with the numerator. So 5 times 4 gets you 20 over BC. So now we are going to multiply BC on both sides, and that'll cancel out the fraction on the left to just get 20 equals 3 times BC. Then we just divide by 3, and we get that BC is equivalent to 20 over 3. That is one of our answers. So, all that work, but now we have a hang on what we should be doing. So, to find that length, we used triangle ADB and ABC. Now let's try using the triangle we didn't use, BDC. So triangle BDC. What could that be similar to? Well, let's try an approach similar to what we just did. So I'm going to cut all this off from the rest because we're doing like a new part. We're trying to find DC now. So BDC, well, it has a 90-degree angle, so it could go with ABC. What other angle in ABC would match up? Well, how about just the angle C? Because both the triangles BDC and ABC match up with the angle C. Since they both have 90-degree angles, we get angle-angle similarity. So to write our congruent statement, we have BD, that's from that top on the shorter side to the right angle. So that would match up with AB. And then C. And notice how the C's have to match up since they are the same values, or they're the same angles. So now we can write a couple ratios along with this. Let's start off with the shorter side of BDC, that seemingly being BD. Well, what is the shorter side of ABC? Like we talked about, it is AB. Now, match up the largest sides. So the largest side across on the right angle of BDC seems to be BC. And the largest side of ABC is AC. And then finally, our last side, so we have BD, BC. Now we need DC over, well, DC is like that medium side, so the medium side would be BC. Just like that. Now, let's try plugging in numbers and seeing what we can simplify. So, BD is 4, and AB is 5. And that must be equal to BC, which is, well, it was our unknown. It's 20 over 3. But I'm just going to keep it as a variable because it's going to be a lot simpler to multiply BC than 20 over 3 and all that. And that matches with AC, but I'm not quite sure what AC is. So we're just going to leave that like that. And then we have DC over BC. Again, we know what BC is. It's 20 over 3. But fractions divided by fractions, it kind of looks a little ugly, so we're just going to leave it like this now. But what I can easily tell is that if I use the 4 over 5, we can solve for what DC is. So we have DC over BC. Multiply BC on both sides of the fraction. So BC on one side. Oh, that looks terrible. BC on one side, and multiply that with BC on the other. So then we get that DC, because these will cancel out, DC equals 4/5 times BC. And again, we can now substitute BC since we know what the value is. We know that we have 4 over 5, and BC is equivalent to 20 over 3. Now, this can be simplified fairly easily because 20 divided by the 5 will cancel out. And then, well, what's 20 divided by 5? You are left with a 4 on the top, which is multiplied by the other 4 on the top. So we get that DC is equivalent to 4 times 4, 16, with a 3 in the denominator. And that is how we would get DC. Now, this is a longer type of problem, and it is a very complex problem. But it is very important to understand how to break these figures down into its component parts, the corresponding sides, and so and so. Similarity is very important for future lessons, and especially this problem alone is going to give us some very, very interesting consequences and results in the future. So it is imperative that you understand how this problem works.